mi nombre es Will y yo soy el instructor por la talleres. Y por la primera video es solo en inglés porque los tópicos es sistema de números, entonces es más difícil porque tiene más descripciones de matemática y ese es más difícil en un otro idioma. Okay, so in the future, I'm going to do my best to switch back and forth between Spanish and English and try to do all of the explanations and descriptions in both. But for the first video, it's just going to be a little bit too much because there's a lot of historical context and descriptions, and it's just a little bit outside my wheelhouse. So the first object that we're going to start with today is going to be the natural numbers, which is this set right here. So la conjunto de números natural es 1, 2, 3, 4 y todos números that are used for counting. And these are the first ones that were developed. They date back historically to the late Paleolithic, where we have found some bones that have notches marked in them, where on different sides they have the same number of notches. So this would stand to reason that people were actually able to count. So we know that this dates back to about 44,000 years ago. So this number system is extremely old. Historically speaking, the next numbers that start to be developed are actually going to be the ones down here, which we're going to discuss fourth, called the rational numbers. And the reason that we're going to put them later on is because they weren't all discovered at the same time. So back in ancient Babylon and in ancient Egypt, you see certain fractions getting developed. So for instance, 1 over an integer, so like 1 over 5. And in Babylon, you see certain things like 1 over 60 because of the type of number system they were using. And they actually expanded a little bit. They were able to do things like 5 over 10 or 7 over 13. But we still don't see a full discussion of all the rationals because they still don't have 0 and they still don't have the negative numbers. So historically, the next thing that comes up after some of the fractions is going to be the negative numbers. And it takes a little bit of time before we're actually able to develop 0. And 0 is kind of a weird number. It's extremely useful because it allows us to have a true base 10 system because you can have placeholders held. You can hold the place for a decimal expansion, or for a higher number like 105, you can put that 0 in the middle that says that we have hundreds, 0 tens, and 5 ones. So the natural progression that we're going to use is a little bit different than the one that was developed throughout history. We're going to simply try to add new things as we go. So we're going to extend each number system as we go. So we start off with the natural numbers, and then we add this one new number, this one new weird number. We add 0 to the system. And now we call this the non-negative integers because we now have all of the positive numbers like we had before with the natural numbers, but we also have this new number 0. Next, we're going to extend backwards. We're going to add the negative numbers in. So not only do we have 0, but we also have -1, -2, -3, and so on. After this, we now have what we call the rational numbers. So these are going to be the rationals. And the rational numbers are going to be all of the fractions. So anything that can be written as the form a over b, where a and b are both in the integers. So these are the integers and naturals. So when we do this, this gives us the ability to create very small numbers and also very big numbers and everything in between. So we have a very expansive set, and this was largely useful for everything that the ancient world needed. It allowed them to build pyramids and to conduct commerce because you had the ability to do half of a piece of fruit or half of a pound of grain or whatever. And this is mostly what's going to be useful until we get much further along. Until, in fact, we get to ancient Greek with Pythagoras. Now, you can ignore this right here. This is just a joke in case Dr. Ocasio is watching the video. You can just ignore that part right there. So the question next that we're going to ask is, are there numbers that are not in the rationals? So obviously we have seen before real numbers. So that's this set right here. We denote it by the bolded R script. So the real numbers are all of what we think of as all of the normal numbers. They're anything that's in the real line. So if I have a line, I've got a continuous bit. We start at 0, we have 1, we have 2, we've got the negative numbers, we have -1, -2, -2. We've got a half right here, 0.5. So we've all the fractions. So the question is there anything in this line that is not a rational number? And what was found by Pythagoras and his followers was there actually are some. So the first one that was found was the square root of 2. And the way that they show that it's not a fraction is a little bit technical and definitely outside the scope of this class, but the basic argument can be boiled down to this idea that if you have a fraction, it is either simplified or something like 16/12, where it can be simplified down to a fraction that is simplified. So all fractions either are simplified or can be simplified. And the argument that was used to show that the square root of 2 is not a fraction is that they showed that if it were a fraction, it couldn't be simplified. So the technical aspects there are a little bit outside of what we're doing, but what they found is that there actually are some numbers in this line that are not in this set. So they're what we call irrational numbers. So what we see, like I said, we keep extending. We started with the naturals. Now the naturals are inside of the non-negative integers. The non-negative integers are inside of the integers. They contain them. This set here is that set there, right? So we're just adding to it. And then we add in the fractions. We add all the little gaps down in here that can be written as fractions. That's going to give us Q, or the rational numbers. And then when we fill the entire line in, we get to R. So we keep adding. And it turns out, and this is outside the scope of, and later in the class we'll see this, but you can actually extend the real numbers and add more numbers in, and you can get the complex numbers. And it turns out that there are other ways that you can add even more numbers and keep going, but these are completely outside the scope of the class. But it's important to note that you can keep adding more numbers. So how do we figure out what type of numbers something is? Well, the negative number, if it's negative right off the bat, we know it has to be. If it's a whole number and it's negative, we know immediately it's an integer, because we don't have negative numbers in the first two sets. If it's greater than 0, and it's a whole number, we know it's a natural number. And if it's 0, then it's a non-negative integer. So that's an easy distinction to make. But when we get to some weirder numbers, it might be a little bit tricky. So, but there's a nice rule that we can follow. So it turns out when you write a number as a decimal, if it repeats, so if you can find some pattern that it does, you can always figure out what it is as a fraction, because you can always just put it over some string of 9s. So for instance, if 4 repeats, it's 4/9. If I have two numbers that repeat, like 13, so 1, 3, 1, 3, 1, 3, I can put that repeat pattern over 99. And in the same way, if I have three numbers that are repeating, 307, 307, 307, I can take that and write it over 999. So what this tells us is that if we see some kind of repeating pattern in our numbers, then we know we must be working within the rationals. Whereas if I have a number like pi or e, pi is 3.14159, so and so and so on, e is 2718828, and it goes on forever. And neither of these will ever repeat. And because we don't see a pattern in the numbers, it turns out that you can't write them as a fraction. So they're not going to be within the rationals. So these numbers here, we would all say are in, we denote with that little e, and then q with the bold. And these, we could only say are in R. Now we can also say that these are in R, so you could write are in Q and because again, Q is inside of R. So whenever I take a number like 5, 5 is in the natural numbers, because it is a natural number, but that also means it's in the integers, it's in the rationals, and it's in the reals. Whereas if I have something that is a fraction, it's only going to be in these two. Or if I had a negative number, like say -6, it's not going to be a natural number because a natural number is only positive, but it would be in Z, in Q, and in R. So that's the basic way for identifying the type a number is. In the next video, we're going to go over different rules that we can use in algebra. Thank you, and